Hello, everyone, and welcome to my channel. This is Sohini from South Bay, California, and I welcome you today. So I know I've been away for some time, and again, work have been become extremely hectic. But I'm super excited to have two announcements for everyone joining me today. First of all, I am now going to be starting live streaming from next week onward. So I am going to be live every Friday night in IST, in Indian Standard Time, and again Friday morning, Pacific Standard Time. And I am going to be releasing short content on machine learning for production. So how would you use machine learning for scalable systems? So the systems that are, would allow your machine learning models to stay on without having, with minimal customer downtime. I'll be teaching you about some of the softwares and how to create CI/CD pipelines and how to build robust, machine learning models altogether. So I'm super excited to be coming live. And again, please watch out for the posts that I will be sending so that you know when to tune in exactly. Right. And the second announcement that I have is again for everyone who's tuning in for the first time. This is the channel where we talk about anything AI and machine learning. And today we are going to be discussing about this common topic that I, hear a lot about is how, what is the difference between transfer learning and retraining? So statistical machine learning models versus deep learning. Let's say you have random forest classifiers and you have already built a particular model on it. Can you reuse this if you have a new batch of data at all? Or is it anything to do with transfer learning? So there are a lot of misconceptions about the differences, and so that's what I wanted to show you with examples today. Always understand the basic difference between the statistical machine learning model and deep learning model is a deep learning model is an ensemble of feature extractor and a classifier put together. So whenever your weights and biases, they are taking care of automatically extracting features, which machine learning models cannot do. You have to give them the best features, and then they will give you the best classifier. So if you are unsure of what kind of features to use, deep learning models are a good way to go. But again, you need a good plethora of data to get started, right? So that's the pluses and minuses of using deep learning versus not. So in today's video, I'm going to give you the major differences of what transfer learning versus retraining is. And I'm going to give you two use cases, and I'm going to be releasing a code base, which is going to be in the description box below so that you can reuse it and you can understand for yourself how to treat batches of data for MLE production. So if this is of interest to you, if anybody you think has interest in this topic and you think this content can be of use to them, please share this video. And otherwise, please don't forget to hit thumbs up and subscribe to this channel. So today we are going to be talking about a key machine learning concept, which is how to reuse pre-trained models. And mostly we know how to do this for transfer learning, where we have large deep learning models that we need to train. So we reuse some existing weights and biases from larger data sets. But how can we also do this for statistical machine learning models? So I wanted to show you examples of both today. So I wanted to start with this key question that I get a lot. What's the difference between transfer learning versus model retraining? So let's first try to understand the why. Why do you even need something like transfer learning plus fine-tuning? So transfer learning, it leverages the learned weights from a prior similar task or data. It eliminates the need to train a large DL model from scratch. So necessarily you will not need a huge data set in order to train millions of these weights and bias parameters. And it also ensures that you will get faster convergence with lesser training samples required. Now, what does transfer learning essentially entail? It means that you are transferring the knowledge of how you're extracting features. So the initial layers of a deep learning model, they are always feature extractors. But you often have to remake the final classifier layer, because the final classifier layer is going to tell you how many classes. Now, let's say ImageNet, it had 1,000 classes, but now let's say that you're reusing those weights for a new data set that has just 10 classes of flowers, let's say. So you always have to retrain or fine tune it for the last layer in order to cater to your new data set. Typical use cases, you will see computer vision and NLP. So we will look at an example of transfer learning in the use case today. And how well what you do is called freezing of the initial layer. So the top layers of a convolutional neural network or a deep learning model, they are actually frozen. That means they do not need to be retrained. And then what you do is you add additional classification layers, or the final classification layer is actually fine-tuned. And again, you retrain on the unfrozen or the new layers that you have now reintroduced. Then let's look at what is retraining. So let's say you have a statistical machine learning model, and it could be support vector machines, or it could be logistic regression, or any kind of classification model that you have. But all of a sudden you see that for new batch of data set, it has poor monitoring metrics. So it's not doing the probability of prediction is not as high as it used to be in the past. And again, in these cases, you typically have to retrain. So with the whole new batch of data set, you have to take a data-centric approach where the model can be changed. So the model is actually not getting improved over time, but your model is actually maybe yesterday a support vector machine was the best solution. Maybe today logistic regression is, and maybe tomorrow maybe random forest or decision trees are the best way to go. So you do not fixate on the model, but you really take care that the data is well analyzed, and the data, the features that you've extracted are the best exemplary features for that particular data set. So here your importance is on hyperparameterization, because you might have to retrain everything from scratch. Now, what is this process typically? So typically, if you are looking at statistical machine learning models, you do look into these concepts of data drift and concept drift. And again, I have mentioned both of them in a video, which I'm going to link in the description box below. But data drift or concept drift is, let's say that you had trained a model or a statistical machine learning model on some particular data set, but now that a new batch of data set comes, you see that your performance are just not the same anymore. So this can really happen because there could have been this data, the distribution of the data is now completely new, so it's a data drift, or it's a concept drift. That means the correlation between your input and the output is not the same anymore. And again, in these cases, you have to raise a flag saying that this metric is really off, in which case you might have to train from scratch. Or most ML models in production, whenever you are having an online monitoring system, you actually have, put these constraints on metrics. You may say the ROC, it should always be above a particular limit, or maybe the maximum and the minimum probabilities of a particular batch of data should always lie within a particular range. If it is not, that means there might be something off. That means either there is data drift or there is concept drift, which needs to be corrected for. And how this can be done, again, you have to detect it using online monitoring. There has to be a pipeline for new data collection, because clearly your ML model is not capable of handling this new data set anymore. So you have to get new data set, and then there has to be either fine tuning or training a new model from scratch. So retraining mostly happens, and it's mostly allocated, corresponding to the statistical machine learning models. However, it could be retraining of a deep learning model as well. So today I wanted to talk about this GitHub that I have now provided, and let's look at this GitHub. So this is the repo that I have. I first wanted to start using the first code that I have available. So let me open it in Colab, and we will run it in this particular use case. So what we are trying to do here is to show how this retraining thing is happening. So just like I mentioned, what is retraining and how can you apply that? So here we are going to be using random forest classifiers for a classification problem, and here we are going to be using the warm start feature, so that as data gets, batches of data gets added, your classifier constantly keeps getting better and better. So that is what we are going to be learning today. So for this case, we will start with a digit data set. It's a handwritten digit recognition data set which has 1797 samples, and again it has 64 features. Let's look at some of the features. So this is how an image 2 looks like. So if I say what does an image 0 looks like, this is what image 0 looks like, this is what image 1 looks like, and so on and so forth, right? And the targets, this is actually the Y labels corresponding to these images. So first of all, what we do is we are going to be splitting this data set into train and test. We are going to be using the train test split from sklearn in order to do that. So let's just look at what is the size. So the training data has 1437 samples and the test data has 360 samples, right? So we have done an 80-20 split. Now what we are going to be doing is we are going to be looking at the training samples in batches. So we're assuming, let's say we only are getting, batches of 500 samples per day, and we want to make sure that my model gets better with time. So I want to be retraining my random forest classifier so that it keeps getting better and better over time. So that is what I am going to be doing here. So here I'm saying that it has a warm start is true. Well, when I'm starting from scratch, there is nothing to start from. But what I'm saying is I'm going to be training random forest classifiers with the maximum depth of 20. And the number of estimators, that means the number of trees that is going to be formed for every single batch is just 20. So I'm just forming 20 estimators per batch. Right, so let's try to do that. So now my random forest classifier has been trained. Now let's try to predict the performance of this random forest classifier on the test data. So the complete test data, and here I see my test accuracy is 95.8%. So not too bad, but not too good either. Now what I'm going to be doing is I am saying that now let's blow up the total number of estimators to 50. So for the first 500 samples, I'm just saying that there were 20 estimators. But now I'm saying let me just take the 500 to the 1000 samples, so the next 500 batch of training data set. And now I'm training in all there will be 50 estimators or 50 trees that will be trained. So now if I do this the same thing, and again if I predict on the same test data, now you see that the test accuracy is actually improved. So it went from 0.958 to 0.963. So you definitely see an improvement for the next batch of data. Now let's try the same thing again. So you have the last batch of 400 something images. So I'm again going to retrain it on the last set, and now I'm getting 0.966. So you see your classification accuracy has actually improved. So this is just one example in which you are essentially aggregating across the different sort of estimators. However, you should also take into consideration what kind of samples are the samples disbalanced. In this case, there are 10 classes of 0 through 9, and each and every one of them have the same number of samples. However, if the number of samples are different, you might have to use gradient boosting to the images that have lesser number of samples. So essentially, using the warm start problem, you can really take care of this retraining in which you're taking care of data in batches, which is a very realistic scenario that happens in machine learning in production. And then you're relearning or reusing the knowledge for your new batch of data and constantly improving your performance. All right, now that we have some understanding of what retraining we refer to by, let's look at an example of transfer learning. And this is the resource that I have pointed in the same repository that I'm going to be releasing with this video. And this is actually called a code lab. And what this code lab does is it walks you very detailed into what is a neural network, how to use a neural network classifier, and what would be the different components of a deep learning model. So for anybody who's starting in deep learning and wants to get more hands-on experience, it's completely free. I'd like you to try it out so that you have a better understanding of what the model typically does. What we will be doing is actually working on this particular collab that you can get. It's called the Keras Flowers Transfer Learning Dataset. And this is essentially the structure of what we are trying to do. So remember when I was talking about transfer learning, I said there would be some the initial layers, they are frozen. They are the ones that you should not be touching. And then what you're essentially recreating or fine tuning is the final classifier layers. And that's your work that you're going to be putting in. So let's jump into the code directly so that, we can get a little more hands-on experience. So whenever you are, trying out something like this, always remember the first step should be save a copy in Drive, because you don't want to be reusing, the version that they already have. And also in this case, you should retrain on a GPU. So the first step would be to connect. And once you have connected, you should, manage, view your resources and change the runtime. You see it's already given as GPU. It's either GPU or none by default. If it's none, then you should change it up. So this is how you ensure that you have GPU for this particular session. So let's start by running the initial layers, the initial lines of this record. So let's look at this data set. So this data set, it's actually a flowers data set in which the image size is 192 by 192, and it is already stored on a Google bucket. So that's where we are fetching this data set from. And if you look at the data set, it has only 16 data sets. Okay, so only 16 images that are available to you that can be split into fewer classes. So ideally the ImageNet dataset, it has been trained on like 1,000 classes, but here of course the number of classes is less. And even you see that the batch of data is also very small. It's only 16 images. So what you want to do is you want to randomly sample. So you want to shuffle these 16 images around with a batch size of 64. So in per batch you have 46 images that will go to training, and the remaining 10 batches are going for your validation run. So first of all, let's run some utility codes. This is just in order to display. So let's try to display the data set. So you're only going to be displaying 9 images from this data set. So these are 192 by 192 images, and this cell is going to ensure that this is the data set you have at hand. So if you see here, the number of classes is actually 5. So you have daisy, you have tulip, you have dandelion, you have roses, and you have sunflowers. These are the 5 category of classifiers. So essentially you are reusing some the weights and biases from pre-trained models, but you have to now reuse them on only 5 categories. That is the problem that you have at hand. So first let's try to get the batches working. So this is done. Now this is where you need to write your own code. So your code will be here, where and all of the instructions is actually given in this lines above. So what you need to do is you are trying to create a sequential model. First, you are going to be using flatten. So the format is tf.keras.flatten, and image size is already given to you. And then you will add a single dense layer with some activations, and then you are going to be using the compile. So all of the lines are actually given here. You just have to reuse it in your code here. So let's do that. So what we are going to be starting with is the pre-trained model that I have over here. And then the next thing that we are going to be having is the flatten layer, right? So like it mentions. So let me just take the flatten layer, and now notice here that I don't need any parameters inside because the pre-trained model is taking care of that. Then the third layer is going to be the classifier layer, right? So this is the classifier layer that I'm interested in, and that's it. So these 3 would be input, and as soon as we have that, and we're done. And the optimizer, the compiler, is Adam. And that's it. So you see now my pre-trained model is MobileNet version v2. The number of parameters is really small, and that's the reason why it's very compatible with mobile versions. And the non-trainable version, because these are the the head of or the feature extractor layers. You've already mentioned that they are not trainable. So as soon as you say a particular section or a particular layers, the model are trainable. If it's false, that means you cannot touch them or you cannot train them. As soon as you make them true, then those will also get modified in the process. So let's start with this model and see what your performance is. All right, so I already have run everything for the MobileNet v2. Now, of course, you see that this is not an optimal model, right? So it's not your training and the validation curves. They are not behaving similarly at all. So let's try some other model here and see if we can get a different performance. So now I'm just changing the pre-trained model, adding a few more lines, and now let's see if this changes the performance. I'm going to call it model underscore 1, and okay, now the training is done. Let's see what the curves look like. And now you see the curves look, at least, the performance is definitely better than what it was before, because now you don't see, the deviating, nature. So both of them, they're constantly, accuracy is increasing for both of them, and losses, consistently reducing. So in this case, you definitely start seeing the improvement where, your final accuracies are way better than the MobileNet, where your, final accuracies, again, all over the place. So in this case, if you had the resources, you should have picked the VGG as a better pre-training model for this particular use case. So this is a very useful way in which you can identify which model to really prepare. And finally, what we need to do is, again, to predict. So in this case, I will try to use model underscore 1 in order to do my predictions. So first of all, I'm going to run the predictions, and then I am going to be displaying them, right? And here you will see that if there were any false positives, they would have been detected in red. So again, this was a good classifier. See, none of them got detected in red. So this was actually doing pretty well. But now, if you had used your MobileNet, now you see, so for the MobileNet, now you see this is just the model. Now you see you get a false positive. So here the class is sunflowers. It should have been tulips, right? So they're just yellow tulips. So this is how you will apply a pre-trained model. And again, Keras has a huge variety of different kind of pre-trained models. These are just some of them. You should definitely check them out. And you should always play with this trainable feature, so that you can unfreeze certain layers, refreeze, and in this way you can run through batches of models. So together, the combination of transfer learning and retraining, if you understand how to use what, that is essentially what you require at the core for a typical machine learning in production use case.